Welcome to the Lensmaker equation tutorial. We're going to talk about first, what is the Lensmaker equation? We're then going to use this equation on an example involving a biconvex lens. We'll then use it on an example involving a biconcave lens. We'll then use it on an example involving a vision correction lens. And finally, we'll conclude. So, let's start off by discussing what is the Lensmaker equation. So this is an equation that defines the relationship between the radii of curvature of the front and back surface of a lens, the index of refraction of the lens, and the focal length of the lens. So we're going to define what each of these terms are. So here we have a lens. Okay, we'll call the blue side the front surface of the lens, assuming rays are coming in from direction, rays of light. We'll call this green surface the back surface of the lens. Now, if we draw a horizontal axis right through the center of the lens, what we can do is, for this back surface, we can draw out a circle, okay, corresponding to this back surface. Now, this circle will have a curvature center corresponding to this back surface, and it'll have a radius associated with the back surface. So this is the radius of curvature of the back surface of the lens, which we will call R2. Now, we can do the exact same thing for the front surface, which we're defining as this blue surface. We can draw out a circle. The circle will have a curvature center corresponding to this front surface. This will also have a radius of curvature associated with the front surface. And we'll call this radius R1. Okay, so now taking this lens, we can discover the refractive index of the lens. Okay, and this refractive index is a ratio of the speed at which light travels through the lens as compared to in a vacuum. So meaning that light will travel faster in air or in a vacuum as opposed to in the lens. Okay, so this ratio of how fast light travels through the lens as opposed to in air is called the refractive index. Now, because light always travels slower in the lens as opposed to in air, this value for the refractive index will always be greater than 1. Okay, and finally, assuming that rays of light are coming to this front surface, these parallel rays of light, after passing through the lens, are going to converge to a single point. Okay, this point is what we're going to call the focal point. Moreover, if we have an axis through the vertical axis of the lens, we can define this distance between this vertical axis and the focal point as the focal length. So, putting all of this together, we get the Lensmaker equation. So, this is the relationship between the focal length, the refractive index, and the radius of curvature of the front and the back surface. Now, when using this equation, it's very, very important to keep sign convention in mind. So by that, I mean that if the front surface is convex, we define this value of R1 as positive. If it's concave, we define this value of R1 as negative. Now, the reverse is true for the back surface. If the back surface is convex, R2 is going to be negative. And if the back surface is concave, R2 will be positive. So now, let's see how we can use this equation in a couple examples. So, in this first example, I want to find the focal length of a biconvex lens, meaning both the front and back surface are convex, that has a refractive index of 1.5, a front surface radius of curvature of 4 centimeters, and a back surface curvature of radius of 6 centimeters. Okay, and we want to find what is this focal length. So, to do this, let's use the Lensmaker equation. Now, we have to keep sign convention in mind. So because it's biconvex, the value for R for the front surface we'll define as positive, but for the back surface, we're going to define it as negative. Okay, so we're given the refractive index is 1.5. The radius of curvature of the front surface is a positive 4. For the back surface, it's a negative 6. And we can rearrange this Lensmaker equation to solve for f, the focal length. Now, plugging in our values, simply we just plug it in. We can find our answer as 4.8 centimeters for the focal length. Very, very easy. Let's do another example. Now, in this example, we're going to use a biconcave lens. So now the lenses are going to be concaved inwards. So the refractive index will be 1.3. The radius of curvature will be 2 for the front surface, and for the back surface, it'll be 4 centimeters. Now, intuitively, just to keep in mind, if we have parallel rays coming into this lens, and this is the vertical axis through the lens, they're going to converge to a point behind the front surface. Okay, so in this case, focal length will be negative. So, to find out what this value of the focal length is, again, we just plug in our values to the Lensmaker equation. So let's check the sign convention. So because it's biconcave, the front surface value for R1 will be negative. The back surface value for R2 is going to be positive. So the refractive index we have is 1.3. R1 will be negative 10 centimeters. R2 will be positive 6 centimeters. And we're going to again solve for F. So again, rearranging the Lensmaker equation, we simply plug in our values and we get negative 12.5 centimeters for the focal length. Very easy. One more example. So now we're going to use a vision correction lens. And so we want to find the focal length of a nearsighted vision correction lens that has a refractive index of 1.5, a front surface radius of curvature of 30 centimeters, and a back surface radius of curvature of 15 centimeters. So, Lensmaker equation, let's look at the sign convention. Because the front surface is convex, R1 will be positive, and because the back surface is concave, R2 will also be positive. So, having our given values, the refractive index is 1.5, R1 is a positive 30 centimeters, R2 is a positive 15 centimeters, and again, we can just solve for F. We plug in our values, and we get the focal length to be negative 60 centimeters. Again, very, very simple to use. So, just to conclude, we saw that the Lensmaker equation defines the relationship between the radii of curvature of the front and back surface of a lens, the index of refraction of the lens, and the focal length of the lens. And just keep in mind, when you use this equation, you have to keep sign convention in play. So if it's a convex lens, R1 is going to be positive. If it's concave on the front surface, R1 will be negative. Now, for the back surface, If the back surface is convex, R2 is negative, and if the back surface is concave, R2 is positive. It's the reverse of R1. So keep these things in mind and enjoy the Lensmaker equation.